his own title.
I would gladly do so. Thank you for introducing me, Jakob. Yeah, I know this title is not very handy, I would say, so I want to say I'm talking roughly about the robustness of deployed artificial intelligence and how to preserve it. And I'm also giving you a practical context with that. So first of all, I want to give you a rough overview of this presentation. And as I already said, we're taking a use case which is predicting a delivery time. And this comes with some problems born by practice. And we want to formulate a solution that we designed. Let's dive right into the use case. We are in the furniture business, in the manufacturing business of furniture, and also the logistics. And this can get quite complex with the value networks involved, with all the suppliers and retailers and also the end customers. And the data, in contrast to how we usually have it, it's not a historic data set. We can perceive it as a data stream, which is potentially endless. The features of that data, they contain, for instance, the products that were ordered, client or customer IDs, as well as the price of the products ordered, the positions, the number of products, and also some location information, so we know how far something has to be delivered after it's manufactured. As I said, we want to predict the delivery time. How long does it take from the point of the order until it's being delivered at the target site? And as this is a continuous measure, this can be mapped as a regression problem. And if you will, the AI lies exactly there in the functional mapping between the data, the features I just lined out, and the target measure, the duration. Nobody is perfect, also not AI, of course. We start with a rather simple model, which is a random forest regressor, and we do no retraining here. We just do a training at the beginning on roughly 40 days of data, which is really not much. It's just a small number of data points, maybe 10K rows, and we get a quite high error in estimation. So this model makes an error of roughly 278 hours, which is roughly 11 days, so quite big actually. And I want to disclaim at this point, there's really a lot to optimize still, but this is not the focus of the presentation. You could do feature engineering, you could do so many things, such as better pre-processing, have some intelligent way of filtering outliers when they arrive. That's not the focus of this presentation, but I want to direct your focus towards the error behavior of that model, which is plotted here. So this is a smooth error from all the batches that arrive, that the model conducts. And what I find interesting here is that the patterns vary quite heavily, one could argue. There are even some peaks, or the niveau of these errors is quite different at points. Of course, this is just 3 boxes I put there, but there are more. You might even make out more subtle or more fine-grained patterns. But something's odd here. So the model seems to be not very robust, so to say, on the data. There seems to be something happening, maybe some kind of change happening. And this might put the AI model under some kind of strain. Let me give you the hypothesis that this is due to concept drift, some destructive impact that happens on the model. Because in a perfect world, we would wish to have a robust model, which is, if we will, in a very general sense, robustness could be formulated as a high and a very stable performance on long times. And not only that, but also if we have more unseen data that we have not seen during training, and it would it would be very nice if this would also hold on evolving data streams. So the notion of change I tried to introduce before, if this would not hamper with the robustness of the model. And if we had a robust model, this would come with a large range of benefits for our problem. We would have inventory benefits and concurrence, competitive advantages, and a lot more. So this would be admirable, actually. But there's something that comes in the way there, and I said it's concept drift. What is concept drift, actually? Concept drift is a product of the reality not being static. We know it, there's always something happening, and this can also impact the data that goes into the model. And concept drift, it can be described as this change happening and as a very destructive influence on the model. You could, of course, describe it in terms of various dimensions, shapes, and colors, but one way would be to distinguish it based on the different targets of concept drift. It might be virtual. In this case, a previously learned models denoted by black lines in this case. Black lines are the models separating these three different classes. It's just a toy example. In virtual concept drift, the data shifts a little, but your model still holds, basically. In the real destructive type of concept drift, this should bother you much more because your model, you need to relearn it, you need to reformulate it to still separate the data well. So this is just one way to separate these different kinds of concept drift. So what can we do about it, actually? There's this research field called concept drift adaptation, and this tries to exactly overcome these kind of effects, this phenomenon, by handling it. And it would be the ultimate goal to actually preserve the robustness of AI out there in the field after it's deployed, even and after training is long over. There's some research attention. It was too hesitant initially, but in the last decade or so, it improved critically, which is good and maybe also motivated from practice as we all start to apply artificial intelligence more and more. And would be a bummer if all of these failed. And but regarding the implementation of these approaches, is still very slowly happening. And there could be really much more implementations in the tools that are used generally. Yeah, so we try to formulate just one response. Of course, there could be many, but we took some inspiration from nature in doing so. And yeah, as you might have guessed, it's a concept drift adaptation approach, of course. And this one, it is explicit. We do not want to just blindly adapt our model without even knowing when should we do it and why should we do it. So we use a concept drift detection algorithm. I'll come to that later. And yeah, we want to take inspiration from nature, especially from evolutionary biology. And this kind of, does the name of this approach is nature-inspired concept drift adaptation algorithm, or NICDAM, as I want to label it right now. And the goal of this is to balance this everlasting dilemma of machine learning, which is plasticity versus stability. So you want to have your model being stable against noise and being deterministic, but at the same time, you want it to be able to still learn new stuff, easily said. And also because typically, the research community mostly focuses or heavily focuses on classification problems. We want to look at regression problems instead and formulate a response specifically designed for such problems. So I give you some kind of schematic of this approach. As famously used, this is an ensemble approach, which is also already some kind of inspiration from nature. An ensemble, which is this region here, it combines multiple single models, which is supposed to introduce some kind of diversity into the model. All of these different AI models in there, they should have a different perspective on the data. At the beginning, you start with the model you brought. It's actually quite open. You can bring your own model. And we want to call it like a stable member. When we go to evolutionary biology, this is like your your first entity and might be knowledgeable because it learned on quite some data already. And then as the ensemble fills up, you can combine all the outputs of these AI models and just, for instance, weigh their outputs and compute the average of it. In that way, you hopefully get a better and more robust estimation out of that. That's nothing new. But the algorithmics that actually control how to insert members, this is something we came up by looking at evolutionary biology. So now you have an estimation. If you wait some time, this problem has the characteristic that the ground truth actually comes at some point because your product is being delivered and you can track that. However, this is much too late when you actually know the duration. For your prediction problems, it's much too late. But you can still use this, you can still leverage this information for computing an error, the error that the ensemble committed, basically. And this is fed to so-called concept drift detection or detectors. And they are specifically tailored statistical tests that try to monitor the error behavior, even if it's a little bit delayed or fairly delayed. It's still interesting to see how the error behaves. If there's some slight abrupt change in this error, this might be a notion of something that we have to do against that. Of course, if the error is going down, we're happy, obviously, but yeah. If the concept drift detector recognizes that change, it might give us an alert, and we can react to this alert and introduce a new member into the ensemble. And this is also where the striving for dominance, as we might observe it in natural populations, comes into practice. We try to have this ensemble as light and not too heavy as possible. And therefore, we want to compare these members against each other, especially these new ones that introduce a fresher and more younger perspective because they learn on newer data, because they start to learn once the concept drift is being detected. They are in competition against the stable one. And if we compare those, you can say which one's actually better based on the metric you choose, which might be some kind of error metric on the problem you're trying to solve. And yeah, if it's better, the stable must go and make some space for a new member. And if this is not possible, we still want to discard one of the younger members and make room for a new one. So we have this new perspective also included in the ensemble. Now we remember initially we had this error, 278 hours, and yeah, it's still a considerable error after applying this NICTAM approach. It's still 110 errors, which is roughly 4.5 days. Still not perfect, far from perfect, but I want to direct your focus towards the relative change. Again, I made this disclaimer. There's a lot to still do, to still improve this measure, although it's already much, much better than the expert can say, because it's such a high customizing environment where the combinatorics get gigantic in making out the different products. So it's really hard to predict how long this takes, and also given the different retailers and suppliers you have, it's really hard to predict, even if you have some years in the business. Yeah, it's much better. It's strictly below the error of our previous approach. Sorry for the contrast, by the way. And yeah, and also we were able to leverage some of the information we took from the error behavior to even iron out those peaks, which is quite nice. And also we were leveraging that information and even get into some very low error regions. And one might argue it's still very rough, but although it's already smooth, but it gets a little bit smoother and a little bit more level. Yeah. Now, this is the performance of this approach. This brings me already quite close to the end of this presentation. I still want to give you some key takeaways, what I want to highlight from what I told you. First of all, I already said it. The world is not static; it's quite dynamic. I think we all know that. We cannot trust in a model being deployed just work for endlessly. And also, I want to highlight that the invested knowledge by the practitioners you do not have to discard it. You can bring your own models. It supports even batch machine learning, which is quite well understood over the years now. And we can just wrap it in such ensemble approaches like this one. So this proliferates the experience being made so far and the learnings. No need to be very disruptive there in my point of view. And also, on the other hand, AI is actually too static if we do not take enough care about it, if we do not monitor about it, because inherently it wouldn't learn if we don't instruct it to do so. This is why really strategies need to be put into practice. At best, we might risk good or mediocre performance, but in the worst cases, we might risk catastrophic failure of AI, and some change might just bring it to its knees, and then, yeah, performance declines. And these are really the three most important points I want to give you for this presentation. And just some words, because I didn't introduce it to you earlier. I'm working for the FZI Research Center for Information Technology, and we are among the foremost institutions for applied AI in Europe. We have a large portfolio of AI research topics, but also we are a little bit broader. And we also have our hands in post-quantum cryptography, robotics, manufacturing topics, mobility and health, for instance. And we do not want to stop at research. We also want to act as a trusted advisor for the practice. So we want to actually do the transfer from the research into practice. And there are some two example initiatives I just wanted to name here, which is Klimaneutral Digital and European Digital Innovation Hub for applied AI and cybersecurity. These initiatives actually deal with alike problems and actually try to tailor customized solutions for the companies experiencing these problems. And they come with AI trainers that bring specific a wealth of data science competences. So that's that. I thank you very much for your attention. If you want to ask some questions, I'm in the panel afterwards, and our booth is quite strategically located right opposite this stage. So if you want to come by, do not hesitate. I would be glad. And yeah, thank you very much for your attention.